Okay, so let's see what we got here with our fundamental theorem of calculus packet. We have a graph in the first one here with negative 2 to 3. Our function is just 3, so we just have a constant function in simplest type. And let's see what happens. It says shade the region bounded by the given curve, the x-axis, and the lines x equals negative 2 and 3. So ultimately they're asking us to shade this part. And fill in the chart by calculating the signed area for each value of x using the geometric formula for area of a rectangle and properties of integrals. So in this particular case, we're going from 0. Notice is our lower limit. So if we go from 0 to negative 2, that's going to give us a rectangle that is 6. But we're going right to left, so this value should be negative 6. Negative 1, we're going 1 to the left here, so that should be negative 3. 0 to 0, of course, is 0. 1 is going to give us 3, 2 is going to give us 6, 3 is going to give us 9. Alright, and in the general formula part here, we're ultimately asking for what can we do to get this formula for big F here. Well, we know that we can do what to these x's and get these numbers here. We're simply just multiplying them by 3. So the general formula would be 3x. Which shouldn't be surprising because that big F is actually the antiderivative of little f here, isn't it? And what's the antiderivative of 3? 3x. Okay. Alright, graph the pairs on the grid below. So we got negative 2, negative 6. I'm going to go by 2's here. So negative 2, negative 4, negative 6 here. Do that same thing here. So negative 2, negative 6 will be right there. Oops, nope, I lied. Negative 2, negative 6. Negative 1, we're at negative 3, 0, 0, we're at 1, 3, and then we're at 2, 6, 3, 9, we can't get on there, but ultimately we have a linear equation, which is again, not surprising. And it says write a linear function for f1 of x that represents the graph from part C. Should match the formula in the chart above. Well, we can see that it is clearly y equals 3x, or f of x equals 3x, because we have a y-intercept of 0, slope of 3. And ultimately in part E, what is the derivative of big F? It's 3. Okay. All right. So again, in this exercise, we were just exploring the relationship between a constant function and its antiderivative. We are going to do very similarly on example 2 here under your worksheet 1. The same function, except for we're going from 1 to x, and we're going to see if does that change anything if we have a different lower limit than 0. Okay? So ultimately, if we go, actually it just says use the same graph, doesn't it? Alright, so we're still using the same graph. But if we're starting at 1, then starting at 1 up here, we're going left over here to negative 2, we're going to get negative 9. Going over to negative 1, we're going to get negative 6, then negative 3, then 0, then 3, then 6. Now, how about a general formula here? We can see by the y values here that it is linear, and that the slope is 3. So it would be 3x this time minus 3. We put a negative 2 in there, we get negative 6. Minus 3 would be negative 9. Same thing with the 1. If we put a 1 in there, we get 1. Here we give us 3. 3 minus 3 would give us 0. So that would be our, oops, get it down there for you. So our general formula here would just be same 3x, same slope, but minus 3. Alright. And let's see if we can answer the questions here. If we graph the ordered pair on the same grid which you graphed the other one. If we go ahead and graph and we do the same deal with the points here, we get negative 1, negative 6. We would get 0, negative 3, 1, 0. We'd get 2, 3, and we get 3, 6, which ultimately would give us the same line, just translated down 3, of course. So writing our linear function would just be 3x minus 3, similar to what we did in the previous problem. What is the derivative? The derivative, of course, is 3. And then part F says compare F1 and F2. How are they the same? Okay. Well, they're both linear, of course. Okay. And they just have different y-intercepts. Okay. So really, bottom line is what does that change in this problem by having 0 as the lower limit and 1 as the lower limit? Okay. Essentially, it just changes the initial value, doesn't it? Changes the y-intercept of the two lines, which ultimately isn't that our c if we were to anti-differentiate here. Just gives us a different value of c. Alright, let's see what happens if we have something a little more complicated like a line. It makes it really hard, because line's much more difficult than a constant, right? Alright, so let's see what happens. We got the line 2t here, going from -2 to 3 again, shade the region. Well, we can see that this part of the region is below, this part of the region is above. And so if we take those triangles and we find our answers here, the integral in g1 here is defined as 0. So 0 going this way would be a 2 by 4. 2 by 4 would make a 4, but it would be negative. Over here we'd have a 1 by 2. And 1 by 2 would make 1. But it's negative again. 0, of course, is 0. Going in the 1 direction here, we'd go 2 by 1. That would be 1. And when we get to 2, we're going to have 2 by 4. 2 by 4 would make 4. And then we get to 3, we have a 3 by 6. So 3 by 6 would make Alright, and as we can see, whoops, you know what? These are both positive, sorry. Those are below and left. We're going left on those because we're starting at 0. So those would be positive. And we can see that if we take all these numbers, what are we going to do to them to get these numbers? That's just t squared. Which again, shouldn't be surprising knowing that, that we know what we know already, which is the antiderivative of 2t would be t squared. Ultimately, the areas are going to give us antiderivative values. Okay. So graphing them on the grid below, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3 9s off the chart here, but ultimately we'd get our parabola as such. G of x would be x squared. G prime would be 2x. Alright, so again, knowing the integral is defined from 0 to x, it gave us just the straight up antiderivative c value being 0 here. Alright, so let's see how that changes if we let it be 1 again like we did with the constant. So if we let that be 1, we're going to need to look at our graph here again. 1, if we went 1, we'd go -1 here, +4 here. Okay, remember this is a 2 by 4, so this would be 4 here, but it's positive because we're going left and it's below. This right here is left but above. And remember, starting point here is going to be 1 for the second part. So this is going to be a 1, and this is going to be a -1, I should say, and this is going to be a 4. So that value should be a 3 in that part. So we should have a 3 there. Going to -1, we're going to get -1, +1. So we're going to get our 0 there. Going from 1 to 0, it's going to give us -1. Going from 1 to 1 is going to give us, of course, back to 0. Going to 2, from 1 to 2 is going to give us the trapezoid this time. It's going to be 1/2 times 1 times 4 plus 2. 4 plus 2 would be 6, times 1/2 would be 3. And in the scheme of things, is it surprising that it was a 3? And ultimately, we're getting a parabola here. There's going to have to be some symmetry once we find that vertex, which we found here. You can see that these are 0s and these are 3s. And then, of course, the next one is going to be a trapezoid as well. Going from here, it's going to be 1/2 times 2, that's 1. And then the addition of these would be 2 and 6, that'd be an 8. So this would be an 8 here. Alright, and the general formula here, we should expect it to be quadratic again. But notice that you can't just square these and get these numbers, but we could square those numbers and subtract 1, couldn't we? That'd be x squared minus 1. So So that means x squared minus 1 here, 2x here. And again, how are these related? They are just a translation of one another. So same graph, just translations. And again, ultimately, what was the culmination of the fact that we changed the lower limit? It just gave us a different c value, didn't it? All right. Okay, let's see what happens this time when we change the upper limit to something other than x. Okay, see if we get anything different result here. So we got the same curve here, 2t. We're going from -6 to 9. And we're going to complete the chart by filling in the areas from of this h of u function, which is the area from 0 to 3x. It says each value of u using the geometric formula, blah, blah, blah. So with that graph, and here's our chart up here, they've given us kind of a head start on this of writing x in terms of u. Right? So that means we can just use u values here. We can change our x values to u values. And remember they told us in that part that u is equal to 3x here. So we know that u is equal to 3x. So that means that this would be a -3, this would be a 1, this would be a 6, and this would be a 9. So if we let our upper limit be 3x, okay, then we can just do our same function that we were given and find the values of h for, instead of -2, -1, and so on, we could do it for -6, -3, etc. Okay? So with this being our picture, and the lower limit here being 0, we're going from 0 to -6 to get our first answer in the chart. So if we go 6 this way, and then we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 down. So that triangle going left is 12 by 6. Times a half would be 36. And we're going right to left, but it's below. So that would make it positive 36 then. Would make that a 36. If we do the same thing going over to -3, we're going to get 1, 2, 3, and then down 1, 2, 3, 4, 5, 6. So it's a 3 by 6. So 3 times 6 times a half would be 9. So, and again, it's positive because we're going right to left. It's below. And then if we do to -1, we've got a 1 by 1. 1 by 1 would be a half. 0 to 0, of course, is 0. And then filling in the other side here, if we go 0 to 1, we got a 1 by 1 again, so that would be a half. Going 0 to 1, we'd have a, or 0 to 3 I should say, which is we're using these numbers. 0 to 3 would give us a 3 by 6 again. So 1/2 times 3 times 6 would give us 9 again. This one would be 36, we know, without doing the work. And this one would give us a 9 by 18. So it'll be 1/2 times 9 times 18 would be 81. All right. And how about a general formula? And what are we doing to these u numbers here to get these numbers here? Squaring them. Okay. So this would ultimately be u squared, if you will. All right. So, and with that said, we're going to graph the ordered pairs here. We can graph them. We're just going to get a parabola. I'll skip that one for now. Write the quadratic equation h of u, and that represents the graph above in part B. And we know that it would be u squared, of course. Okay. And then what's h prime at u? H prime at u would be 2u. Okay. Now here's the upshot of the whole deal. Ultimately, if we want to relate this to x with our chain rule, how does it work with x? So by substituting u equals 3x, define h of x. So h of x would be 3x all squared, which would ultimately be 9x squared. And the derivative of h of x would be 18x. All right. And remember, just going back before we finish that last part, from what we know about the fundamental theorem, okay, we know that if I wanted the derivative of this h function, it would be the derivative, it would be the integrand evaluated at the upper limit, right? So it would be 2t, in other words, 2 times 3x, which would be 6x, times the derivative of the upper limit. What's the derivative of the upper limit? It's 18x, isn't it? We got 6x already, times another 3 would get us to the 18 we needed. Right. So again, the purpose of the exploration is just to show that the fundamental theorem is in fact true based on our numerical analysis here. We get exactly what we thought we'd get. Because again, according to the fundamental theorem, we should have got 18x for the function's derivative, and what did we get? Exactly that, we got 18x. Okay. All right, and so I guess the conclusion then is this, that if we have h of x and that our function is, our upper limit is g of x, some other function, okay, then the derivative of that function is the integrand evaluated at the upper limit times the derivative of the upper limit. That's what this is in symbols, isn't it? Okay. This is the integrand evaluated at the upper limit, and this is the derivative of the upper limit. And in function notation, again, it's the f of g of x. Okay? And so with that said, okay, what are we really using here? Well, what do we recognize that as? That's simply the chain rule, isn't it? Okay. So when we differentiate, or when we differentiate an integral function, okay, we're just using the chain rule again. When we have anything other than x, okay, as our upper limit, okay, we're using the chain rule as part of that fundamental theorem. Okay, we'll stop for there today, and we'll start on worksheet 2 tomorrow. The